All right, in this little demonstration, I'm going to take a mirror. So we've got one mirror here, we've got another mirror here. The reason I chose these mirrors is because they're very flat surfaces. I needed to have flat surfaces. And what I'm going to do is I'm going to push this one mirror, you can see just one mirror against the other, and I'm going to hold it there. They're dry, so there's no surface tension or anything like that, but I'm going to hold it there, and you'll see it sticks for a while, right? It's not coming off. And it actually takes a little bit of force to pull it off. I'll try it one more time. So you can see it's actually stuck, and then it finally falls off. Now the question is, why does that happen, right? The other thing is true the opposite. If I drop the mirror and I dropped it perfectly flat, there it's not very flat, but if I dropped it perfectly flat, it would actually come to rest on the surface of this mirror very gently. In fact, they do this with big panes of glass. It's called free falling of glass, where they'll take a big pane of glass and then drop it this way, and it won't shatter. And the reason for that is because what happens is as the glass gets close to the surface, it pushes the air out of the way and it provides some cushioning. And the same sort of thing happens in reverse. When I have the glass up against the surface and I let go of it, air has to rush in the gap between the two pieces of glass, and there's very low pressure in that gap, and so there's a net force that holds this mirror up against the surface until the gap gets big enough. I'll go through some analysis on this. It basically involves differential control volumes, conservation of mass, and the linear momentum equation, but you can show that there'll be a net pressure force on this pane of glass between the small gap in the surrounding atmosphere that holds the piece of glass up there for a little while. So I'll do that in the rest of this video. Okay, so let's model the situation. And rather than work this problem out from scratch, I'm going to refer to a solution I worked out previously where I typed it up nice and neat. And the reason I'm doing that is because it'll just go faster that way. If I worked from scratch, it would just take a very long time to get through it. So the first thing we're going to do is just model the two mirrors as two parallel disks. So by doing this, I make the problem axisymmetric. It's just a little easier to deal with. It'll still show the important features of the flow that I want to highlight. So we have these two parallel disks. They have a radius r, capital R, and they're separated by a very small gap height h. The top disk is going to be fixed. The bottom disk is going to move downward at a constant speed v. And so the h will increase with time. And we're going to assume that this h is very small compared to r. So I say that right here, r is much larger than h. We're going to say the disks are immersed in an incompressible Newtonian fluid and that the pressure far away is P infinity. So that's the pressure far away. The whole thing's immersed in the fluid, so there's fluid in between the disks as well as kind of on the outside. And we'll go ahead and ignore gravity. You can ignore this part that I've written down here. This is just for solving the problem if I wasn't going to step you through it. If you're going to solve it on your own, these hints would be helpful. So since we're dealing with a viscous fluid, we're going to make use of the Navier-Stokes equations. And in particular, the directions that we're going to be interested in are the r direction, so that's the radial direction from the center line, and then the z direction, which goes from the bottom plate upward. So we're going to write out the Navier-Stokes equations in cylindrical coordinates in both the r and z directions, so they're complicated. These we get just from a formula sheet. And we're going to make a few assumptions to simplify them. The first is that we're going to deal with an axisymmetric flow, so that means all the d theta terms will go away. So you can see there are a few d theta terms here. And then we'll also assume that there's no swirl component to the flow, meaning that the flow is not going around in circles around the disk. So that means that the u theta terms will be 0. And then, of course, no body forces of significance, so that the g sub r and g sub z terms will ignore. And those are reasonable assumptions. And then if we make those assumptions, then these two equations will just simplify here. You can see the d theta terms and the u theta and the body force terms all disappear. So here we are now with our Navier-Stokes equations in the radial direction and the z direction. And then the next step is actually an interesting one. It's done a lot in lubrication flows. It's a scaling argument based on some of the dimensions of the problem. And in particular, we said that the gap height is very small compared to the radius. So h is much, much smaller than r. It's a very thin gap. And this would be the case when the discs are very close together, like when the two mirrors are pressed up really close to one another. There's a very small gap between them. You know, the surfaces aren't perfectly smooth, so there's a little bit of a gap. And then as the gap starts to grow, h is still very small for some period of time compared to the radius of the discs. So we're going to look at that part of the flow just when the discs are very close together. So h is much smaller than r, and it's also reasonable to assume then that any sort of dimension in the r direction will be of order capital R, so that this is just a characteristic dimension of the flow. So you can see in the radius direction, just as a characteristic dimension in that radial direction, we'll use capital R. Similarly, a characteristic direction in the z direction, we'll use a little h. Right? So a ddr would be a characteristic gradient in the radial direction would be like scale as 1 over r. Similarly, a gradient in the z direction, like d over dz, it would scale something like 1 over h. Right? So then when we go ahead and look at the viscous term, let's say this viscous term up here in equation 3, this is the viscous term in the r component of the Navier-Stokes equation, just one of the viscous terms. So if I expand that viscous term, so if I take the derivatives and expand it out, it'll look like this. So this is just expanding these derivatives. And I use my scaling argument, you'll see that, first of all, we have the velocity ur in each one of these. And then this will be like the velocity in r over capital R squared. This one will also be like u sub r over capital R squared. Same thing here, u sub r over capital R squared. So the whole left-hand side will scale something like 1 over r squared. This term, the d squared ur dz squared, that's this second viscous term, will scale like ur over h squared, because it's d over dz scales like 1 over h. So if you look at that for a moment, the left-hand side will be like u over r squared, whereas that's the left-hand side. The right-hand side would be like u over r h squared. And so you'll see that this term will really dominate. So again, let me highlight it. This yellow term is kind of like this term. It's just sort of the order of magnitude scaling of it. And then this green one is like these terms. So basically you see that this d squared ur dz squared will in general be much, much bigger than this viscous term. And so what it means is that we can eliminate this term from our equation. It's just going to be much smaller than the other viscous term. And you can do a similar thing for the z Navier-Stokes equation. You can do that. That's what this line is. It's the same kind of argument. This is the first viscous term that's right here. It's been expanded out. Here's the second viscous term right here. And it's the same kind of argument, but just for the uz component of the velocity. So this term can also be neglected because it'll be much smaller than the second viscous term. So if we make those arguments, then our equations 3 and 4, our Navier-Stokes equations, can be simplified a little bit further down to here. And we're going to actually simplify it even further. Now, before I go ahead and do that, one of the things I want to do is make use of the continuity equation, or the conservation of mass equation at a point. And the continuity equation for an axisymmetric incompressible flow will look like this. This just comes from the formula sheet. Just conservation of mass at a point. And I can expand out this derivative. That's what this is right here. And I'll go ahead and make some scaling arguments here as well. So the z velocity will scale something like the capital V. Remember that capital V is just the downward velocity of the disk. So I would expect then the velocities in the z direction to be of the same order of magnitude as capital V here. It's a characteristic velocity in the z direction. So that's what this is. And so if I make use of that along with my previous scaling arguments, so this term here, for example, would scale something like V over H, right? And then the d over dr is like 1 over capital R. Here's another R, that'd be like 1 over R.
So if I rearrange this equation and look at the scaling for UR, it'll scale something like R times V over H. Okay, so that tells us kind of the relationship between these velocities. So you can see here U sub Z scales as V, U sub R scales as R V over H. Since H is very, very small, you can quickly see that U sub R will be much larger than U sub V just in general. And that's given right here. So with that in mind, we can go back up and look at these two equations, and what you'll find is that everything in this Z Navier-Stokes equation will be much, much smaller. Like all these terms here on the left-hand side will be much smaller than the corresponding terms in the R component of the Navier-Stokes equation. Similarly, this term here, this viscous term, will be much smaller than the corresponding R component in the Navier-Stokes equation, the same viscous term. So basically, all of the terms in the Z component of the Navier-Stokes equation are much smaller than the corresponding ones in the R component of the Navier-Stokes equation, which means that the pressure gradient in the Z direction will be much smaller than the pressure gradient in the R direction. So again, we can make these arguments through these characteristic dimensions. So what that means then is we won't worry about the pressure gradient in the Z direction. Pressure gradient in the Z direction is just how the pressure changes in this kind of vertical direction. It's so small compared to the pressure gradient in the radial direction that we'll just ignore it. So we'll say the pressure only varies in the radial direction. So it's nearly constant in the Z direction. Okay. Now we'll do some more scaling arguments. The next thing I want to do is consider the magnitude of the inertial terms. So let me go back up to the equation here. So what I mean by inertial terms are these terms here. So what I want to do ultimately is compare the magnitude of these terms to the magnitude of the viscous term. So for example, let me just pick one here. This term. The magnitude of this term would be rho times the magnitude of U sub R, which looks like this, R times V over H. I'm just getting a characteristic size of that term. And then that'll be multiplied by another U sub R, so this thing again, divided by a capital R, because it's D over dr. And that would give me the magnitude of this term times the density. And I can do the same thing for this term, and I can do the same thing for that term. So this is what they look like when I expand it. Here's that first unsteady term. Now in this one, I have a ddt derivative. The characteristic magnitude of that would be like the velocity over h. This just tells me how fast things are changing with time. Just kind of rough order of magnitude. It's just the downward velocity divided by the gap height. Those are the characteristic dimensions here. So you can see we have a rho times d over dt. That'd be like 1 over, let's make sure I have that right. Yeah, it'd be 1 over h divided by v. And then the u sub r we did before from the continuity equation right here, be r v times h, or v over h, sorry. So the characteristic size of that would look like this. Then here's the first convective derivative term on the left-hand side, and we can look at the scaling for that, and it comes out to have the same sort of characteristic size. And then we can do the third term on the left-hand side, so it's the second convective term. And it turns out to have the same kind of scaling. So all three of these terms over here, all three of these have the same characteristic size. And they all have this, the characteristic size looks like this. Now let's do the same thing for the viscous term on the right-hand side. So it's this term right here. So you can see that'll be a mu times the u sub r, which is given here, divided by h squared, because it's d squared over dz squared. So that'd be like 1 over h squared. So that's done right here. So this is the magnitude of that viscous term. There's the mu. D squared over dz squared term is like 1 over h squared, and the u sub r term is here. So this will be our characteristic magnitude for that viscous term. Now let me take a look at the ratio of the inertial to viscous terms. So here's the inertial terms from the left-hand side. Here's the viscous term from the right-hand side. By the way, remember that the ratio a characteristic inertial force to a characteristic viscous force is like the Reynolds number. And you can actually see that here. When I take the ratio of these, you end up with a Reynolds number looking term. It's the Reynolds number based on the gap height h. So when that Reynolds number is very, very small, what that means is that the characteristic viscous force term dominates. And this would be the case when the gap height is very small, right? We're dealing with cases where h is really, really small, so that Reynolds number based on h will be very small. And that means that this term, the viscous force term, will dominate over these inertial force terms. So with that in mind, this entire left-hand side of the equation will be much, much smaller than that term when that Reynolds number is small, which is the case when the gap height is small. So that means we can reasonably neglect the left-hand side here. So what we'll be left with is this expression here. Okay, so this is just our Navier-Stokes equation now in the radial direction after we made a number of scaling arguments. And these scaling arguments only really hold true when that Reynolds number is very small, which will be the case when the gap height is small. Now, you might ask yourself, why do we still have the pressure gradient? It's the pressure gradient that's really driving this flow. If we didn't have the pressure gradient, then we wouldn't really have any flow going. So it's the pressure that has to overcome those viscous forces and keep the flow going. So that pressure gradient will have the same size roughly as the viscous force terms in order to keep the flow going. So we have to keep that one in there. So now we have a much simpler differential equation than what we started with. Just again, this is the radial component of the Navier-Stokes equation. So really, ultimately, it started way up here with this equation. And we used some assumptions and some scaling arguments to shrink that equation all the way down to this form. And it relies very heavily on those scaling arguments. Well, this is an easy equation to solve. We can integrate that twice with respect to z, and we'll get an expression that looks like this. Now, notice when we integrate that, the PDR is not a function of z. We made that argument further back here, right? So we said that the pressure really only varies in the r direction, not in the z direction. So that's why when we integrate, we can treat that as a constant with respect to z. So when we integrate this equation twice with respect to z, we'll get this kind of expression. Here you have, because it's a partial derivative, when we integrate, we'll bring in some unknown functions of the radius. So I just call them f sub r and g sub r. The way you can sort of think about this is if I worked in reverse, if I took the partial derivative of u sub r with respect to z twice, these terms would just disappear, right? And again, it just, they only come into play because this is a partial derivative. When we integrate with respect to z, there could be some unknown functions of r. Now, to find what those unknown functions are, we have to apply some boundary conditions. And the two boundary conditions we have are the no-slip boundary condition at z equals 0 and z equals h. So that is, let me go back up again. Z equals 0 is right along the surface of this bottom disk. Z equals h is on the surface of the top disk. So we have the no-slip boundary condition on those surfaces. So that means the radial velocity at z is equal to 0 is 0, and so that means the g sub r is going to be 0. And then the radial velocity when z is equal to h has to be 0. So that means the function with respect to r is going to look like this. And then we can combine them together, and so this will be our final expression for the radial velocity. It's a parabola. It looks like a Poiseuille flow is what it ends up looking like. Just flow between two flat plates, basically caused by a pressure gradient. So that's what the velocity profile in the radial direction looks like. Now, ultimately, I'm trying to find how the pressure varies in the gap and the kind of force we need to apply to the disk in order to move it. So I'm going to go a little bit further here. We still don't know what this pressure gradient is, so we're going to have to solve for that. And the way I'll do that is I'll make use of the conservation of mass relation. So, and you'll see how this works in just a moment. So what I'm going to do is I'm going to take a control volume that looks like this. It's just a small axisymmetric control volume. It's a height h in the vertical direction, so this direction is h. And the distance out this way, it's a little hard to see, but it's r. and I'll apply conservation of mass to that. So here's conservation of mass. This is the time rate of change of mass in the control volume, so there's their time rate of change. The mass in the control volume is the density times pi r squared, that's just the area of the disk looking from above, times h, so that gives me the volume of the cylinder here, defined by that red dashed line. When I take the time derivative, it's only the h that's varying with time. And the dh dt is just v. Remember that this is h and the v is headed that way, so if dh dt is positive, meaning the height's getting bigger, that corresponds to the velocity, v. And then this second term right here is the mass flow rate out of the control volume through the control surface, so that mass flow rate's just going out through these sides. So we'll integrate that over the height h, so that we're integrating from z equals 0 to h. Here's the density. The velocity relative to the control surface coming out is just the u sub r, just the radial velocity. That's this velocity right here, u sub r. And then the height through which it's, or the area through which it's flowing is going to be 2 pi r. That's the circumference going around, kind of the outside of that disk. It's like a circle looking from above. Times dz, which is just a little bit of height in the vertical direction. Just keeping in mind that u sub r is a function of z, right? We saw that right up here. That's why I have to integrate. So I can do that integral and simplify it down. I haven't substituted in for u sub r yet, but let me just leave it as u sub r. And you work through some math and you'll get this expression. Now what I'll do is I'll substitute in for my u sub r into here and work it out. And when you do all that, you'll get now an expression for the pressure gradient in the radial direction. So this is how we find our pressure gradient, is we apply conservation of mass. And just a couple of things to note with this pressure gradient. First of all, you'll see that when V is positive as it's directing downward here, this pressure gradient is positive, meaning that the pressure, so if V is positive, then dPdr is positive, which means that the pressure when r is equal to capital R will be greater than the pressure when r is equal to 0. Because dPdr being positive means that the pressure is growing as we go in the radial direction. So that means the pressure here will be larger than the pressure here. Right? So the pressure is decreasing as we move inward. And the other thing is that the pressure gradient really gets big as h gets small. Remember, we're dealing with small h values, and as h gets increasingly smaller, that pressure gradient gets bigger and bigger. So it's very sensitive to the gap height. Okay, so now we have this pressure gradient. We can substitute that back in right up here. So let's go ahead and do that. And this is what happens when you do that. So this is what our radial velocity term will look like. So you can see here's the parabolic kind of expression, and you can see again it's very sensitive to the gap height. Now ultimately I want to find the pressure and the force involved. So I want to find so this tells me the radial velocity at any position. But what I really want to find is, notice there's a radius in there as well, so it's a function of both r and z. But really what I want to get is what the pressure is at any radius. So to find that, what I'm going to do is go back to my pressure equation here and just rearrange that and solve that differential equation. So this is that equation just rearranged. I brought the dp to one side and the dr to the other side. I'm going to integrate. In this case, I'm going to integrate from where r is equal to capital R to some arbitrary radius. So I'm actually integrating. Let me go back up to the picture. I'm going to start here where the pressure is P sub capital R, sorry, it's the pressure right at the very outlet, and I'm going to integrate to some arbitrary location in here, little r, or actually let me make it consistent with the picture. Some arbitrary location here would be P sub little r. And the reason I'm doing that is because I'm going to apply a boundary condition to that very end point. So that's what this derivative here is here. I'm starting from the very edge of the disk and working to some arbitrary point on the interior. So here's the edge of the disk, some arbitrary point on the interior. And when you work through that math, you now get your expression for the pressure. So this is getting very close to what we ultimately want. And when you look at that, you'll notice that R is always less than or equal to capital R. So this term will be negative. V is positive, headed downward. So that means that the pressure at some arbitrary radius will always be less than the pressure at the edge. So again, the pressures, we talked about this before when we talked about the pressure gradient right up in here. So the pressure is decreasing as we go inside. And in fact, it goes parabolically. If I sketched it out, so here's radius, here's capital R. We'll start with some P sub capital R, and then as we move on so it'll be capital R when we start there, and then as we move toward the interior, let me just make sure I have that correct. Yeah, it'll be negative. So it'll look something kind of like this. So it'll be the largest pressure on the exterior. Little r is equal to capital R, it'll just be P sub R. And then when little r is equal to 0, this one will be P sub capital R minus 3 mu v r squared all over h cubed. That's this point right there. So you can see that the pressure decreases as you come inward. And actually, right now I've been working the problem saying that there's just some fluid that's in between the discs. If it was a liquid, one of the things you'd have to be careful of is if that pressure or any pressure crosses the vapor pressure, if it decreases below the vapor pressure of the liquid, then that fluid could cavitate. And that's actually an issue when you're dealing with bearings. This kind of geometry is actually a common kind of thrust bearing design. So if the vapor pressure, let's say, was right here for the liquid, then this whole region right in here would actually cavitate, and it would change the system that we were modeling. So anyway, that's a concern sometimes with bearings. If we're dealing with a gas like air, then you don't have to worry about that sort of thing. Okay, so now we're to the point where we're very close. We still don't know what P sub R is. So in order to find that, we're going to have to apply some boundary conditions. Actually, one last thing before we do that. Getting to this point, actually, I've been saying that V is greater than 0, that the disks are separating, but I could still apply this equation if you were pushing the disks together. In that case, the V would be negative in that case, and so then the highest pressure would be at the center of the disks, and the lowest pressure would be at the edge. So this equation applies whether the disks are moving apart or coming together. So let's talk about that boundary pressure, P sub R. And I'm going to start first with the disks being pushed together, kind of shown in the picture in the bottom right here. So now the disks are being pushed together, so the flow is being squeezed out. In that case, the pressure right at the edge of the disk, the P sub R, would actually be the same as the surrounding pressure, P infinity. And that's because these jets here coming out are free jets, and so they have the same pressure as the surroundings. And so in that case, the P sub R would just be P sub infinity. So that's what our pressure distribution would look like in that case. This is for the case when the disks are being squeezed together. And if you wanted to find the force required to squeeze those disks together, excuse me, we can integrate the pressure force over the whole surface of the disk. So we'd have the pressure times the area over which it acts. Remember, these are disks. So looking at it from kind of an angle here, you know, they're circular disks. So the area, I'm kind of looking at it from above. This area at radius r, that little bit of area would be 2 pi r dr. So the pressure is constant over that little area because the pressure is a function of radius. So that's what that little area is here. It's just the circumference of that ring times the thickness of the ring multiplied by the pressure, and that gives you the pressure force. And by the way, I'm writing out the pressure force in terms of the gauge pressure. I don't have the P infinity here because you'd have P infinity acting on the bottom, and so I'm not going to include the P infinity here because they would cancel. So I'll just work in terms of gauge pressure, so that's 0 gauge pressure out here, and then on the interior I just get rid of the P infinity if it's a gauge pressure. So anyway, so I can substitute in for P here, assuming a gauge pressure, so I get rid of the P infinity, so I'm left with that term. And then I integrate that, go through some math, and ultimately here is what my force looks like to squeeze the two discs together. Keeping in mind, you'll see a negative here, but keep in mind the V is negative because it's actually pushing the discs up together. So the whole thing will be positive. So you can see that we have to apply force to push the disc together. And the reason we have to apply that force just physically is because we're squeezing the fluid out, and there are viscous stresses because of the no-slip boundary condition on the top and bottom surfaces. So you have to overcome those viscous stresses. So you have to apply a force vertically in order to squeeze it out. And you'll see that as H gets smaller and smaller, that force goes up very, very quickly. So as you press this together, it gets harder and harder to press it, increasingly closer. I had mentioned, I believe in the video when I did the example, that sometimes there's a technique called free falling of glass, where basically, let me draw it up here, you have a flat surface, and they'll take a large pane of glass like this and then just drop it down. It'll fall on the surface. So they call it free falling glass. And you can find, there are videos of this on the web. So do a search for free fall glass and you'll see videos of people doing this. But they'll take large, big panes of glass, drop them, and they don't shatter when they hit the ground or on that surface. And the reason is because this is a very flat surface. As the glass falls, you're squeezing the air out. It's not exactly the same geometry here, because here I have parallel plates, here it's kind of tilting, but it's the same exact concept. As the glass pane falls and gets close to the surface, you're having to squeeze out this viscous fluid, and it ends up increasing the pressure in this gap region, and so it applies a force to the glass to decelerate it. And as that gap gets smaller and smaller, the force gets bigger and bigger, and it just helps decelerate the glass. So it's not a sudden shock to the glass when it falls against the surface. It's constantly being decelerated, so it won't suddenly impact the surface, and that's how they keep the glass from shattering. And you can see a similar analysis here. Now, this is for squeezing the plates together, but what happens in our case when we're pulling the bottom plate down? Now in this case, the boundary condition's a little different. So up here we had a free jet where the gas was being squeezed out. And we know that for a free jet, the pressure in the jet is the same as the surrounding pressure, P infinity. But when we're separating the plates, so the bottom plate is moving down, we're actually pulling fluid in from the surroundings. It's no longer a free jet. So the pressure right at the boundary is not the same as P infinity. It's actually different. It's a different boundary condition. Now, in order to find out what the pressure is at the edge here, what we'll do is we'll actually apply Bernoulli's equation to find that. So we can't use Bernoulli's equation in the gap because the viscous stresses are too significant there, and you can only use Bernoulli's equation when there's negligible viscous stresses. But we can use Bernoulli's equation on the outside. So what we'll do is we'll have P infinity out here, where the velocity is essentially zero, it's stagnant air, and then we'll follow a streamline until it goes all the way up to the edge. So we can apply Bernoulli's equation along that streamline outside the gap and use that to find the pressure right at the edge, at R is equal to capital R. So in order to do that, I need to know what the velocity is right at the edge. And there's a velocity profile rather than an actual single value for the velocity. So here what I'm doing is I'm using the average velocity at that little r is equal to capital R radius. So I'm just taking the actual velocity profile, this parabolic profile, and I'm going to integrate it up over the edge. So I just did it over the entire disk circumference and over the entire height to find the average velocity. And so that's what this whole expression is. And in the end, this is what the average velocity is at the edge. And that's the velocity I use in Bernoulli's equation. So here's Bernoulli's equation. The point way out here, P infinity, pressure is P infinity. The velocity is, of course, 0. And then here's the point right at the edge. Pressure there is P sub r. The dynamic pressure there is 1/2 rho velocity squared. This is the velocity at the radius r, and I'm using just the average velocity. So that's been substituted in. And you can rearrange that equation to solve for the pressure at the edge of the disc for the case when you're moving the bottom downward. And then I substituted that back in to our expression right up here. And then we're left with this expression for how the pressure varies in the gap between the two discs. And you can see here, oh, just by the way, note that V is greater than 0 here, so that because the discs are separating. And you can see that the pressure is below atmospheric pressure. It's below the P infinity for the entire length, because this term, of course, there's a negative here. So that'll drop it below P infinity. And this one, little r is smaller than capital R, so this whole term will be negative. So you can see the pressure in the gap is going to be less than atmospheric pressure everywhere, which means that you have to apply a force downward to separate the discs. And to find that force, we do the same kind of approach we did before, where we just take the pressure times a little bit of area and integrate it. And when you do that, this is what the pressure force looks like. It's negative because we're having to pull it downward. You can see there's a term that comes about because of Bernoulli's equation. This density term is because of this part of the analysis to get to the pressure at the radius. And then you have the viscous term. Now when the gap is very small, the viscous term will dominate, because you see it goes as 1 over h cubed, and here it's 1 over h squared. So the viscous term will dominate when the gap is very small. But anyway, the point is that you have to apply a force in order to separate those plates. And the smaller h is, the larger the force is. So that's why when we had our two mirrors against one another, and I pressed them together, and gravity's acting downward, this bottom plate didn't immediately fall. It took a little time for it to fall. It actually stuck onto the surface, and it's not because of surface tension or electrostatics or anything like that. What's happening is that there's just a flow of air trying to fill into that gap, but the pressure inside that gap was very small. And so you had a net force acting upward on that bottom disc to hold it in place. And until the gap got large enough, as the gap gets large, then this force decreases. And so the plate stayed stuck until the gap became large enough that this force balanced with the weight of the mirror, and then finally it would fall after that point. So that's the analysis for that very simple demonstration. You can see it gets quite complex. This is a classic kind of lubrication problem. Lubrication problems in fluid mechanics appear when you deal with very small gap heights. And you can make these kind of scaling arguments that I did in this kind of analysis. But I wanted you to see that, here's something that we see in the real world. The small, the mirror kind of sticking to the surface of another mirror. Doesn't fall right away. Why does that occur? How would you actually model it? And that's exactly what we did here to do the analysis. One other interesting application of this, this is something that my former PhD advisor had told me about one time in a class. Occasionally, aircraft will fall off of aircraft carriers. So, a plane comes in, takes off or lands at an aircraft carrier, misses the aircraft carrier, the pilot ejects, plane goes into the water and eventually sinks to the bottom of the ocean, or maybe just a plane crashes in the ocean, gets to the bottom of the ocean. So, give me 1 second here. Okay, here we go. So let's say we have the ocean bottom here. Plane has landed on the bottom of the ocean, and maybe it's upside down or something, but the wings are very close to the surface, or the bottom surface of the ocean. So this is my plane. It's maybe upside down or something like that, but it's just a sketch, obviously. So when they want to recover these aircraft from the bottom of the ocean, they'll sometimes attach like a cable to the airplane, maybe in a couple of locations, and then try to pull the airplane upward to bring it back to the surface. And what they found is that the forces were quite large in this cable. The tension in the cable was initially quite large, and it could damage, for example, the wings when they first started to lift it. And it was only during the initial stages of lifting. And the reason for that ultimately was because of this exact problem we were just talking about here. The wings adjacent to the bottom surface of the ocean just looked like these kind of parallel plates. And when they were trying to lift it up, this produced this kind of lubrication layer where the fluid had to rush in underneath the wings into this kind of region, and they got a very low pressure region down here, and so it was a very large force, particularly when this gap height was small. But once they got far from the ocean bottom, then it was no longer an issue because they didn't have this kind of lubrication layer to worry about. But anyway, it was an interesting problem that I remember my advisor telling me many years ago. Just something they observed when they were trying to recover aircraft. And you can see here, by the way, when you look at this force term, it's related to the viscosity of the fluid as well. So when you're in water, the dynamic viscosity is going to be a lot higher than if you're dealing with air. So you can imagine you can generate some pretty large forces when you're trying to lift this up and potentially damage the wings. Okay, so I think that wraps it up for this example, so we'll end it there.